our next aim is to understand a little about how the equation-free patch scheme works. And we'll do this in perhaps the simplest possible example. The aim here is to predict a field u of xt on a large domain x between minus h and plus big H when the field satisfies the diffusion equation, du by dt is 2x derivatives of u, with boundary conditions that u is 0 at x is plus or minus h. And we're going to make that prediction by solving only that PDE on the patch between x's minus little h and plus big H. And solving only on the patch is equivalent to doing a computation only on that patch. So, here is a diagram of the domain, and the simplest thing we can do is to discretize the domain from minus h to big H with just a 3-point macroscale grid. So we'll define x1 to be minus h, big X2 to be 0, and big X3 to be plus h. And then at each of these grid points, the field is going to have some value. So at minus h, the field big U1 is going to be 0 by the boundary condition that u of minus h is 0. At plus h, the field u3 is going to be 0 by the other boundary condition. And then the interesting place is at the midpoint, x2 is equal to 0, where the field is going to have some value u2 that's going to evolve in time. Alright, now, the problem is that we're going to solve only on that patch, so let's define the field that we're going to find. We're going to find little u2 of x of t for x between minus h and h, and that field is going to satisfy the diffusion equation. So the PDE is du by dt of u2 is 2x derivatives of u2. And the thing about this PDE, we're solving it in the domain minus little h to plus big H, is we need boundary conditions. So where do they come from? The answer is they come from interpolating the large-scale solution. So our large-scale solution goes from 0 to u2, whatever that is, back down to 0 again, and the classic prediction when you know those three things is you fit a parabola. So the parabolic interpolation says there is a big field, u of xt, which is of size u2 of t, and parabolic going to 0 at x is equal to plus and minus big H. So it has to be this shape, 1 minus x squared over big H squared. Now what does that parabola do? What it does is it makes a prediction at each end. It's at plus and minus h, it says the large scale field should be this value and this value. So what we do is we say that we apply that value at the edges of the patch. So in other words, we're saying that u2 at plus or minus ht is equal to this interpolated field, whatever it is, at plus or minus ht. That interpolated field, we've got a formula for it now. It's this parabolic interpolation. That's u2 of t into 1 minus x squared, but x is plus or minus h, and plus or minus h squared is just h squared over big H squared. Now this combination little h on big H occurs a lot, so we'll give it a symbol. We'll call it R. So R is little h over big H. And because this patch scheme is of most interest when the patches are small, R is typically going to be a small number, much less than 1, like a tenth or a hundredth. Alright, now this turns into boundary conditions from the patch because what is U2? Well, U2 is the value of the field at x is equal to 0, and we're solving a PDE for little u2 in this domain, so clearly what we want is that u2 is little u2 evaluated at 0 and time. In other words, this value, big U2, is the value we're predicting in the patch at x is equal to 0. So replace this U2 by U of 0t, U2 of 0t, into 1 minus r squared. Let's write the left-hand side in again. And then what we've got here is a rather interesting problem. Right, we've got partial differential equation on the patch, subject to this condition, which is an effective boundary condition, u2 plus or minus ht is u0 t into 1 minus r squared, but it's a very unusual form because it's non-local. It's connecting values of u2 at plus or minus h with the values of the midpoint 0. So now our challenge is, how does solutions of this behave? Does it make reasonable predictions for the original problem? Okay, now in this problem we can do things with that. We can solve this equation, and our classic method of solution is separation of variables. We substitute the field u2 is x of x by t of t. So the first thing to do is to substitute this separation into the PDE. Now, fortunately, this is an exercise that you've done before and several times over, and you know what the result is going to be for this diffusion PDE and this substitution, and that is a pair of ordinary differential equations, and one of them is that t dot plus lambda t is 0 in terms of a separation constant lambda, and the other one is the space equation that 2x derivatives of x plus lambda x is 0. Now the new feature here is these boundary conditions. How does this separate? And it's quite straightforward. Substitute into the boundary condition, and it says that x of plus or minus h t of t has to be 1 minus r squared x of 0 t of t. This has to be satisfied for all time, and there's two ways to do that. One is to have t is equal to 0, but then u2 is 0, which means we have no interesting solution at all. So we reject t of t being 0, and what must then happen is that we must have x of plus or minus h has to be 1 minus r squared x of 0. And this is a pair of funny boundary conditions for the spatial structure. But before we get to solving that, let's have a look at the time equation. The ordinary differential equation for time is just t dot plus lambda t is 0, and you've seen this in all sorts of scenarios, and you know that the solution is that big T is proportional to e to the minus lambda t. That is, the separation constant lambda here is a decay rate. And we'll see that again in a minute. Right. Now let's have a look at the space problem and see how that constrains the lambdas. Okay, now, in principle, we have to look at all possibilities for lambda. We have to look at negative, positive, 0, or complex. However, that's a lot of detail, and I know there are only positive solutions for lambda. So we will only consider lambda being k squared for some real k bigger than 0. Now, if lambda is k squared, this is x double dash plus k squared x is 0, and you also know solutions to that ordinary differential equation. And furthermore, you should just write down the general solution. And the general solution is a sum of cos kx and sine kx with arbitrary constants c1 and c2. That satisfies the differential equation. Now that all that's left is to satisfy the boundary condition. So let's have a look at this for this general solution. Firstly, x of plus or minus h is c1 cosine plus or minus kh plus c2 sine plus or minus kh. Cosine of plus and minus, that's the same thing as just cosine. So that's c1 cos kh. And then sine of plus or minus is plus or minus sine. So it's plus or minus c2 sine kh. It's the left-hand side of this condition. The right-hand side is 1 minus r squared x of 0. With this x, that is c1 times cos of 0, which is 1, plus c2 times sine of 0, which is 0, and that's all times the 1 minus r squared factor. And so this simplifies to just c1 times 1 minus r squared. And the boundary condition is that this has to be equal to that. So let's write that down. c1 cos k1h plus or minus c2 sine kh is equal to this. But pull that over onto the left-hand side, minus c1 to 1 minus r squared. Has to be 0. Now these are two equations, one for the plus case, one for the minus case. We can simplify it by firstly looking at the addition of those two equations. So add them together and we get 2 of these and we get 2 of these, but this plus or minus when added together gives us 0. So the net result is 2 times c1 into cos kh minus 1 minus r squared is to be 0. And then a second equation we can get by subtracting the two cases here. And when we subtract the two cases, this c1 cos term vanishes, as does this c1 1 minus r squared, but this sine term reinforces. Plus case minus the minus case gives us 2c2 sine kh is equal to 0. Now we need both of these to be satisfied, and we want non-trivial c1 and c2. So there's two ways that can happen. When sine of kh is 0, c2 can be arbitrary, or when cos kh of 1 minus r squared is 0, c1 can be arbitrary. And if neither of those two are 0, then c1 and c2 have to both be 0, which is not interesting. So our next challenge is to see what the consequences of having sine kh and cos kh minus 1 minus r squared is 0 are. So to look for non-trivial solutions, we need sine kh to be 0 and cos kh is equal to 1 minus r squared. So sine kh being 0, we know what the solutions of that are. For positive k is pi, 2 pi, 3 pi, and so on. So if let's draw these on the kh axis, starting at 0, going to say 4 pi, 2 pi, pi, and 3 pi. So sine kh is 0, at all these points and so on. Now, what about the case cos kh equals 1 minus r squared? Well, let's draw a graph of cos kh. Starts at 1 and it oscillates. Goes down to minus 1 at pi, plus 1 at 2 pi, minus 1 at 3 pi, plus 1 at 4 pi, and so on. And we want to know when this is equal to 1 minus r squared, but remember that r is meant to be a small number, ratio of the patch size to the domain size. So 1 minus r squared is just a little bit less than 1. So let's draw it in there. And we're looking, so there's the value. And we're looking for where that is equal to cos of kh, namely these points. And each of those intersections give a useful value of kh. So we come down and find these values of kh also give non-trivial solutions for C1. Now, let's give these names. This will be K1H, K2H, K3H, and so on. And these are all possibilities. Now, out of all of these possibilities, they break up into two groups. There's this one all by itself, and there's all the rest, all of these. So let's have a look at all of these first. In particular, let's have a look at the first one. So K2H is equal to pi, so that says K2 is equal to pi over h. What does that say? It says the corresponding separation constant lambda 2 is equal to pi squared over h squared. And remember the time solution, that implies the time must vary according to e to the minus pi squared over h squared t. So the decay rate is pi squared over h squared. And the thing about that is, remember little h is the size of the patch, that's meant to be small, so this lambda, this decay rate, is very large. So this decay is very rapid. Right, so it's not of interest to the long-term dynamics. And in fact, all of these modes are very similar. So all kh bigger than or equal to pi are similar. They all correspond to modes that decay like 1 over something over h squared. They decay very rapidly, and because they depend upon little h, they're all about the patch, and they're nothing about the large-scale dynamics. Right, now the one mode for which that doesn't apply is this very first one, K1H. So let's have a look at that. Right. So K1H, that is relatively small. And it must be small because 1 minus r squared is nearly 1, so this intersection must happen for small kh. Now when K1H is small, we can approximate cos. Right, so I do that on the next line. So cos K1H is approximately, from the Taylor's series of the cosine, 1 minus a half K1 squared h squared. And this condition says that that should be 1 minus r squared. Now if you look at that, the 1's cancel, the minuses cancel, and we're left with a half k1 squared h squared has to be approximately r squared. Take the square root, 1 over square root of 2 k1h has to be approximately r, and rearrange for k1. K1 is root 2 r over little h, which is root 2 over little h, times r. Now remember, r is little h over big H. Now you see the little h's cancel, and k1 is approximately root 2 over big H, which leads to lambda 2 being approximately 2 over big H squared. And that leads to the time dependence being proportional to e to the minus 2 over h squared t. And now you see this time dependence is decaying, but it's decaying on something that's characteristic of the macroscale domain. So it's this which is our prediction of what happens over the macroscale. It's this which predicts the decay of this parabola. Now, how good is that prediction? Well, considering the crudity of this single patch assumption on the domain, it's remarkably good. Go back to the original problem and ask what is its solution. The u of the exact original that corresponds to this mode is the decay of the mode cos pi over 2hx, because it's that cosine will be 0 at plus or minus big H, times the exponential of the corresponding decay for this wave number, which is pi squared on 4 all over h squared t with a minus sign. So what we've got here is that in the patch scheme we've got a decay of that mode with a decay rate 2 over h squared, whereas the exact solution is decay with pi squared on 4 divided by h squared. And since pi squared on 4 is approximately 2.5, that too is a reasonable assumption to 2, approximation to 2.5. So the predictions of the patch scheme is working reasonably well, as I said, given this crudity. And that gives a hint that this equation-free patch methodology can work very well given enough patches in complicated situations. Isn't that great?